Welcome everybody, good afternoon. This is Faster, Safer, Better Ranges. Hello. All right, so let's test, is everybody awake after lunch? Who would like faster, safer, better ranges? Yeah, because that's a really fair, balanced question, right? Like, there's just one person back going, no, I'll have these slower, worse ones, please. Hopefully, you will enjoy this talk. Hopefully you will like the proposal or the library I'm going to talk about. And hopefully you've had a good conference generally. I mean, I've had a really great 3 days. And I think one of the things that I really love about coming to conferences is that I get to meet a lot of people who I feel are quite a lot like me. That's not meant to be an insult. I get to feel like I'm amongst my people, right? And if you are like me, you might spend quite a lot of your time watching conference talks, even for conferences you're not at, like online, right? On YouTube. Anybody spend? Yeah, that's most of the hands. And in particular for me, because I'm interested in ranges, I tend to I watch just about every ranges talk there is going. And just recently, or in fact over the last few years, I've noticed a bit of a theme in these talks. And perhaps you have as well. So here's a talk from Jonathan Becara in, I think this is CPPCon 2020. And he's talking about his alternative ranges library called Pipes. Moving on, here's Barry Revsin, CPP Paris 2021, talking about his alternative ranges library called Rivers. CPP Now 2022, here's Arno Schoedel from ThinkCell talking about ThinkCell's alternative ranges library. Here's me from this very conference 2 years ago in that room next door talking about my alternative ranges library. Was anybody in that talk, by the way? I need your back. Okay. Not to be outdone by me, Google had a go. Here's, who is it? John Bandella at CPP Now last year talking about Rappel, Google's alternative ranges library. Daisy Holman, CPPCon last year, talking about her alternative ranges library called Daisy Chains. Yeah, I thought that was good. And here's Joaquin Lopez talking about his alternative ranges library using standard CPP just a couple of months ago. And not to be outdone, here's me again. There was some poor person who I just said, please can you take a photo of me just before this started? And he's like, why? All right, here's me back again talking about a kind of a redesign of my ranges library called Flux. So you might get the idea from all of these things that ranges is, absolutely terrible. And perhaps some people might tell you that's true. I'm not one of those people. Right. Okay, so where was I? I was talking about ranges. I love the feature set that the ranges brings us, right? It allows us to do what I call, or sometimes gets called sequence-orientated programming, right? This idea that we use these higher order operations, filter, transform, and so on, to build up these data pipelines. So ranges offers that, and I think that's great. And I think if the choice is ranges or nothing, then ranges is great. Okay, but there are legitimate problems with it. And almost all of these problems largely stem from the underlying iterator model. And so I don't know if you've watched any of those, 8 or so talks before. All of them, including mine, they follow the same format. In the first 20, 30 minutes, the presenter will talk about what they consider the problems with ranges that they want to solve. And there's a very good reason for that, is because we as presenters, we kind of have to make you care, right? We have to explain, this is the problem, this is the solution. It doesn't really work otherwise. So guess what I'm going to do now? But I'm not going to spend too long on it because, as I say, there are already quite a lot of talks out there that will point to various problems with the ranges library that authors think that they want solved. So I'm going to look at two little examples. So the first one, pretty simple. What I want to do is I want to print the even values in some vector. Okay? Some vector of ints, print the evens. And we can do this. So this is a very simple imperative loop. This is if you weren't thinking about it, if you just like bashed it out, this is probably what you do. But of course, we are 21st century ladies and gentlemen. We want to use all the fancy new stuff. So we decided we're going to use range views for this. Okay, so we're going to use the filter view. Okay, there are a few ways you could format it. This is one way. So we set up our filter view, and then we use the range for loop to iterate over that view. Okay. So now what we're going to do is we're going to play the role of the compiler. We're going to kind of de-sugar all of the ranges stuff and kind of find out what's going on behind the scenes. Okay. So the first thing we want to do is we want to de-sugar the range for loop. So very roughly, it expands to something like this. This is not precisely what it is, but it's close enough for our purposes. Okay, so we set up the begin and end iterators into our view. And while the iterator is not equal to the sentinel, not equal to the end, we print the value, and then we call operator ++ on the iterator. Okay, so pretty straightforward. But now let's think about what the filter views iterators actually need to do. Because the way iterators are specified in C++, they separate the read and advance operations, operator star, operator ++. Okay? And this means that C++ iterators begin on track. That is, when I call begin, provided it's not equal to end, I can immediately dereference it. It has to be ready to go. And this means that when we call begin on the filter view, it has to do some work. It has to run away and go and find the first element that satisfies the predicate. Okay? And again, when I call the increment operation ++ view iter at the bottom on the filter iterator, it has to run away and find the next even element in this case. Okay? This algorithm, this thing it has to do of, iterating through until we find a value, that algorithm has a name. That algorithm is find if. So we can substitute in a couple of calls to find if, like this. And now, of course, we can go and look up the definition of find if and substitute that in. And if we do that and we expand it all out again, well, we end up with something that looks a bit like this. So the first while loop is for our begin, okay? So we have to, before we've even entered the main loop, we have to go and find the initial value. Then we actually do the print that we want to do, and then we have to have a nested while loop where we go and run away and look forward to get the next even value, okay? So I don't know about you, but this is a lot more code than you might expect. Because if you wrote it kind of naively, even after you've expanded the range for loop, it looks roughly like that on the right-hand side. We're getting a lot more code. So two loops, kind of nested loop, it's all a bit messy. Now, perhaps this doesn't matter. Perhaps a sufficiently smart compiler could see through all the extra loops, sort all this clutter out for us, and we get the same performance. You can kind of guess I probably wouldn't be talking about it if that were the case, right? Because that's not the case today. So here is an example courtesy of Mr. Godbolt's wonderful website. This is a very slightly different example. So rather than printing elements, I'm now summing up the elements of the even elements of a vector, just because it demonstrates my point even better. So the top loop is just me doing it kind of the very naive way. The second loop is using the filter view. And so on the left is the dumb way, if you like. On the right is the smart views way. And you can see that on the left-hand side, although it's more assembly, it's a whole load of lovely vectorized SIMD instructions, right? The auto vectorizer has been able to just see what we want to do and optimize that. Whereas, I mean, Matt will probably be able to tell me, but I don't even think the code on the right-hand side is very good. I think even if the vectorizer didn't get involved, this is not a very good way of doing this. But maybe I'm wrong about that. So, okay, the filter view kind of has poor code gen, right? Due to this, really fundamentally comes down to the fact that iterators separate out the advance and read operation. That's what it comes down to. Filter has poor code gen. Maybe we don't care because like filtering is only what, like 80% of what people want to do with ranges. So no. Yeah, so this isn't great. There are various other problems people like to talk about. There's just one I wanted to highlight because I came across this very recently, and this I thought was really unpleasant. So this example is courtesy of Nico Jasutis. Now, is Nico in the room? No. Nico's had a lot to say about ranges. I don't agree with all of Nico's criticisms of the ranges library, but I will say that when I saw this example, he definitely had a good point. So this is it's from P3725. I don't think it's published yet, but Nico gave me permission to use this example. So what are we doing here? Okay, so we've got our array of city names, Amsterdam, Berlin, Cologne, LA. Then we're setting up this pipeline where we're filtering, retaining the cities with large names, that is 5 characters or more, so Amsterdam, Berlin, Cologne. We're reversing that. We are casting all of those to R values, so doing a standard move, and then putting all of those into a new standard vector. So we're moving the 3 large strings into a new vector. So our expected result, hopefully you'll agree, is that the new sub-vector contains Cologne, Berlin, Amsterdam. Okay, does that make sense? Okay. Again, probably by the fact I've put expected results, gives you a clue that this might not be what happens. Can anybody guess what does happen here? UB is correct. Zach might have you seen this example? Okay, so that's so what actually happens is that iteration overruns the bounds of the cities array and starts reading arbitrary data from the heap and trying to copy it into a new vector. This is really bad. I expected like a gasp, but you're all like, yeah. Half of the course, isn't it? So Zach was at the committee meeting last week, and he said the committee, SG9, I guess, gasped at this. So yes, this to me is a really problematic example because there is nothing, I think you'll agree, there is nothing obviously wrong with this pipeline. This is just composing some standard library adapters in a way that we feel as end users should probably work, right? And in order to understand why this doesn't work, you pretty much need to be an expert in ranges and how these things work behind the scenes. And I kind of am an expert in that, and it still took me like an embarrassingly long time to actually puzzle out what's going on. So it would probably take like a significant chunk of the rest of the talk to go into great detail about it, but the very short version is that the filter view has a precondition that you cannot modify elements in such a way that it changes the result of the filter predicates. But that only really bites you if you're doing multi-pass iteration. Okay, so the as R value is moving strings, so it's modifying them, right? Because calling size on a move from string is actually valid, but it's going to return you 0. And the kicker is that views reverse actually does hidden multi-pass iteration. It actually secretly evaluates the predicate more than once for reasons we might get to nearer the end of the talk. So this is, I think this is pretty bad. Just by way of a spoiler, but also just to get you interested in what's coming up. In Flux, the current version of Flux that you can go and download from GitHub today, this crashes with a bounds check violation, so it doesn't start reading arbitrary data, it crashes, which is still not great, but the future version of Flux that I'm going to be talking about today, this works, it does exactly what you want it to do, what you will expect it to do, so yes. So having done the traditional, there are some problems with ranges, let's move on to talking about a ranges alternative, because that's the good bit, right? So what I want is a library for this sequence-orientated programming that is competitive in performance with handwritten loops, right? Like you can always handwrite. You can if you know more about your data, you can always win by really drilling down. But I want something that is broadly speaking going to be as fast as I would expect, if you know what I mean. I want something that offers good safety by default, right? Bounds checking, please. I want a library that, as far as possible, bearing in mind that we are in C++, is easy to use, is predictable, doesn't have unpleasant surprises like we saw on the last slide. And finally, I want something that is as compatible as possible with existing STL containers, existing STL algorithms, right? This is pretty much essential if we want any sort of adoption. I can't just go and tell people, right? So you can't use vector, you can't use map anymore, you've got to use all this new stuff. So this, these are my goals, this is what I want. And if you were here or if you were in that room 2 years ago, you would have heard me talk about a library I wrote called Flux to try and meet these goals. And at the core of Flux was the idea of using bounds-checked cursors as an alternative to iterators. So most of the problems in ranges stem from iterators. If we just change iterators for these bounds-checked cursors instead, things get better. But the other thing that Flux did, and this was kind of an afterthought, to be honest, it's just something I noticed that I could do, was that it provided this internal iteration fast path, right? That when you, for certain combinations of algorithms and adapters, we would switch to using an internal iteration model and things would just get really fast. So in terms of interoperability with ranges, all Flux sequences were automatically ranges, so you could just start using Flux sequences with any old range algorithm you wanted. And in the other direction, all C++20 contiguous ranges were automatically, you could just use them with Flux, right? So vector, span, string view, etc. So this is good. However, for ranges that were not contiguous, Flux didn't really offer any additional safety beyond what ranges did. And the reason for that is we can't sort of retroactively add bounds checking to iterators for something like an unordered map, for example, or a standard list. Okay, so just a little aside, because I saw some confused faces when I just said this. Internal iteration. Put your hand up if you know what I mean when I talk about internal iteration. Some sort of wavy. All right, well, it's easier to start by talking about external iteration because that's what we're familiar with, okay? So external or pull-based iteration is the way in which almost all programming languages present their iteration model, right? And the idea is that we have some sort of sequence object that holds some values, and we have some function like next, for example, where we say, okay, we pull a value out of this sequence, we use it, we do whatever we need to do. Okay, we finish with that one, we pull the next value out, we use it, throw it away, and so on until there are no values left. Okay, pull-based iteration. So we, that is the people doing the iteration, are kind of in control of doing the actual looping. Okay. An alternative method of doing this is what's called internal or push-based iteration. Okay, so the way this works is that you can think of the sequence as being in charge, right? So the sequence, you'll typically have a function like for each, and we, the users, will say, okay, sequence, please will you call my function with each value that you have, okay? And when you do this, it puts the sequence itself in charge of actually doing the looping, and it means that whatever means of doing this is most optimal, you know, it can kind of be hidden behind the scenes. And it gives, in general, very broadly speaking, more opportunity for optimization. So this is a very broad generalization, but we can say that external iteration is more powerful. That is, it can be used in more circumstances. We can implement more algorithms using external iteration. That's why almost all programming languages use it by default. I think Ruby is probably the only exception to this. But internal iteration is more easily optimized. Okay, so that's your like 2-minute primer on what internal iteration is. If you're interested in knowing more about it, there's this really good blog post from 2013 that I highly recommend reading. So I'll put the slides up later, and you can click on that. Okay, so I've talked about flux and cursors and things in the past tense, and that's because I have come up with a new version that fixes some of the problems with the existing library, right? Some of the things that didn't work too well that I've, decided we needed to do better. So what were the lessons that I learned from Flux? I'm going to call them V1 and V2, by the way. That's not the same as the version numbers you'll find in GitHub, but for the purpose of the talk, it just helps us separate out the old version and the new version. So first of all, internal iteration results in absolutely fantastic performance, right? So it turned out, I thought, like my goal with writing Flux was all about the safety, the bounds checking, like safety and iteration. It turns out that this thing that I did kind of as an afterthought was everybody's favorite feature about Flux. Everyone's like, oh man, I tried your library and my code got so much faster. It's like, yes, and it's safer. And they're like, oh, is it? Okay. So internal iteration was great, but the library, well, V1, was not designed around this. As I say, it was kind of an afterthought. And internal iteration, in general, is hard to use when we need to pause and resume iteration. This is when I said external iterators are more powerful. It's because we are in control. We can pause iteration and just come back later and pull another value whenever we like. And in particular, in the Flux implementation of this, it was quite easy to accidentally fall off the fast path, right? So if you knew what you were doing, which I think is probably just me, you could choose to structure things in such a way that you knew you were always going to hit the fast path. But if you were, if you were not so much of an expert, it's quite easy to accidentally drop down. And the other thing I should say is not on the slide, I don't think, but the other thing is that, oh no, I'll tell you in a second. Right. So, next lesson learned is that cursors are really, really great interface for multi-pass sequences. That is forward ranges. This is where we have some notion of position when we're iterating, okay? So if you think about what an iterator for a forward range is, it marks a position in a sequence. And we can, for forward ranges, we can copy the iterator, and that kind of saves the position. We can come back to it, and we can, for forward ranges, have multiple iterators that are iterating at different speeds, right? And cursors, that's good, but iterators have these safety problems. Cursors give you all that, but are much safer. For forward ranges, that is multi-pass iteration, cursors are great. But as with ranges, trying to generalize this position-based model back to single-pass iteration, where for streams there really is no notion of position, this causes problems, right? We saw this causes problems with the filter view because we have to have a separate operator plus plus and operator star, leads to bad code gen. This was the case in Flux as well, unless you're on the fast path. And that's the thing I was going to say a second ago, is that when you're on the, there was actually a semantic difference between being on the fast path and not. Like, it wasn't just your code got faster, you could actually notice it in terms of how many times functions were being called and stuff. So that wasn't ideal. I mentioned it before, but the lack of support for, in particular, node-based containers was a major barrier to adoption. So every time I gave a talk about the old version of Flux, the number one first question anybody asked was, yes, but what about standard list? What about standard map, right? Understandably, because the other way around, I would probably have been doing the same thing. But on the plus side, people really, really like using a dot to chain pipelines together rather than a pipe. So I don't know if you know, I wrote a blog post talking about, well, basically what I'm talking about today, the plans for Flux. And one of the things I suggested was that I was going to start using pipes instead. And there was, I was inundated with people saying, don't do it, it's a terrible idea. So the dots are staying if I possibly can. Okay. So let's talk about Flux v2. Here's the big idea. Cursors are great for multi-pass iteration. Internal iteration is great, but the library wasn't really designed around it. So how about we try a new approach? We have separate interfaces for single and multi-pass iteration. So we have an iterable interface that is based around single pass iteration using a new and improved and more powerful and actually designed this time internal iteration scheme. And we have a collection concept, a collection protocol that is more or less a cleaned up version of what we were doing in the previous version of Flux. So freed from having to also support single pass, we can do things in a slightly cleaner way. All right, big disclaimer. That's a big disclaimer. The following represents the current development version of Flux, right? So I've been working on this for like probably a year. Like, I've done dozens and dozens of different prototypes, testing different iteration models, trying to work out the best way of doing this. And I came up with something I liked, and then I thought I'll propose a talk for it. I saw the talk got accepted for this conference, and I thought that's great. Now I've got a deadline. And then I remembered I'm a software engineer, and deadlines are sort of optional, right? So I was hoping that I would have a release that you could just go away and download and try out. That's not the case. It's still the development version. So there might be some details change between now and when this eventually gets released. But on the plus side, it means that if you do have any feedback or suggestions or want to tell me I'm an idiot, this is a really good time to do it. Okay? Right, with the big disclaimer out of the way, let's move on to looking at the new iteration, the new single pass iteration model, the iterable model. And in fact, let's drill down and talk about how it actually works at the low level and talk about something that's called an iteration context. Iteration contexts. So in the new model, these are the heart of what's going on. These are the things that are actually doing the work. You can think of an iteration context as sort of roughly equivalent to an iterator in the STL, or but it's probably closer to a Rust iterator if you're familiar with that, right? It's the object that's actually doing the work, right? So if you want to implement the iterable protocol, you have to write an iteration context. So they're responsible for actually doing the work. So how do we go and write one of these things? What does it look like? Well, it's got to provide two things. It's a class, it's a type with two things. So first of all, we need a member type def called element type. Right? Makes sense, right? We need to know the type of the thing that we're iterating over. Okay, the second thing, a little bit more interesting. We need an iteration context to have a member function called runWhile. And what runWhile does is it takes a predicate, a unary predicate, that is a function that returns true or false, a Boolean function, a unary predicate, and returns a flux iteration result. So this is an enumeration that tells us what happened after we after we iterated, after we finished iterating. Okay. So the runWhile function, the clue is in the name. What does it do? It blocks. It starts looping. Right. It generally has a while loop inside it, and it calls the predicate for each element in turn. This is the internal iteration, just as we were talking about, right? But rather than just taking a void function, it takes a predicate. And this means that we can pass information back the other way. So if the user's predicate returns false at any point, we stop iterating. runWhile stops iterating, it returns, and in particular, it returns a result of an iteration result incomplete, right? We have not reached the end. You interrupted iteration. You, the user, interrupted it. Iteration was incomplete. Otherwise, if that doesn't happen, if we just run out of elements, we return iteration result complete. Okay? Happy with that? Here's the really key thing, though, the most important thing, and I probably shouldn't have put it 2/3 of the way down the slide. Should have made it bigger, right? If iteration is incomplete, that is, if we broke out of it, we can resume iteration from where we left off, from the next element, by calling runWhile again. As long as we haven't modified the iteration context or modified the underlying sequence, we can resume iteration with another call to runWhile. And the important thing about this is that we're not required to pass exactly the same predicate the second time. So for example, we could have start iterating with just a really simple predicate that just examines each element, and we just skip elements until we reach one that we care about. And at that point, we pause iteration and we swap in a new predicate that actually does some heavy lifting for the next 10 elements, right? And then we're like, okay, I've had enough of that. We pause iteration again, and we go back to the skip. So this is really pretty powerful. And yes, you can do that with iterators today, but this has the added benefit that we have the internal iteration optimization opportunities as well. So iteration contexts are expected to store any necessary state that they need to enable this pause and resume to happen. Right? This is really, really crucial. So iteration contexts, they will typically hold a reference to their parent iterable, their parent sequence, right? As well as I say, any necessary iteration state. So iteration contexts are reference types, like iterators. And I said iterators are bad and unsafe. But the difference between iterators and iteration contexts, even though they're both reference types, is that contexts are typically, or are expected to be, non-copyable and non-movable, right? This is because I hate you, but no, it's because it's like, I'm not kidding. Deliberately, it makes it very difficult to use an iteration context as anything except a short-lived local variable, which is precisely what they're intended to be, okay? That's not the only reason. The other reason is because there are other tricky questions like, okay, if I pause iteration and I move the context and then I resume iteration on the new context, is that valid? I want to avoid, questions like that. So we're just going to say, no, in general, you can't copy or move a context, right? Use them, short-lived local variables. You can't return them from functions. You can't, So yes, as I say, this helps prevent references kind of escaping into the wild as iterators do. Iteration contexts, although it's what I've been talking about, they're mostly an implementation detail, and end users will generally, so people who are doing 95% of what people do with ranges, or 99% of people do with ranges, just putting together pipelines and calling some algorithm at the end, you're never going to see an iteration context, right? It's good to know what's going on behind the scenes, but it's not something you're going to be dealing with day to day, unless you are actually writing iterable adapters, or in some cases, algorithms. All right, so let's have a little look at what an iteration context actually looks like. So here, I've got an iteration context that just generates us some ints. Okay, so from and to, so this is pretty much like standard views iota, except we're just limiting it just to ints here and not worrying about being unbounded. Okay, so what do I need to provide here? I need to provide an element type. So in this case, the element type is just an int. In general, element types can be references or object types. Either is fine. In this case, I want to return an object type. And then I need to provide an implementation of run while that takes an arbitrary predicate. So what does run while need to do? Well, it needs to have a loop inside it, okay? So while current is less than bound, so we're going to continue iterating while this is true. And then what do we want to do? We want to call the predicate with our current value and break out if that predicate returns false. So if the predicate returns false, we return iteration result incomplete, and otherwise we return iteration result complete if we eventually reach the end. Okay, and one thing you'll notice is that I call predicate with current plus plus. So this means that we're always, even if the predicate returns false, we're always ready to go at the next iteration, right, with the next element, just as we're required to do. Okay, everyone see what's going on here. Okay, I'm going to make this very slightly more complicated, but only very slightly, right? There are a few more angle brackets are coming in. But don't panic, because it's basically the same. Here is an iteration context that works for any forward range. It is basically identical to what we had before, except that instead of a pair of integers, I'm using an iterator and a sentinel. But the loop, everything is basically identical to what I had before. Every range is iterable using this iteration context, right? Like I'm not simplifying anything for the purposes of the slides. This is like pretty much, maybe I took away some namespaces, but it's pretty much lifted directly from the code. This is for forward ranges. For input ranges, if you're wondering, it's very slightly more complicated because we don't have the pre-increment operator plus plus. So for input ranges, we have to do one other little trick. We have to store a flag indicating if we broke out of the loop, we have to, next time we enter the loop, we have to do, start off with doing an increment. But again, simple enough to do. All right. What can we actually do with iteration context? Well, funny, as strange as it sounds, not all that much. We could call run while on them, right? So we have this wrapper function run while, and all of this does is call ctx.run while. Okay. Much more interesting is this function, next element. So what this does, next element, you give the context, pass in a context, and what it does is it returns you an optional containing the next element in that sequence from that context. If there is one, otherwise, if we've reached the end, it returns you an empty optional. So how does this work? Well, it works like this. So we start off with an empty optional, then we call run while, and we pass it a predicate that, if the predicate is called, it emplaces the value into the optional, and then immediately returns false. So returning false from the predicate, remember, breaks out of the loop. So we stop iteration after one element. And it turns out that because this is just a really simple lambda, if you pass this lambda into run while function like the ones we've just seen, the compiler can see, hey, you're passing in a function that immediately returns false. I'm always just going to break out of the loop. I don't even need a loop. I don't need any jumps or anything like that. This compiles down. The compiler can see straight through this. This works really, really well. And this function, this next element function, allows us to single step through sequences. Yes?
You said your element type supports references. So
yes.
Which kind of optional are you using that supports references?
So the Flux library has its own optional type at the moment that supports references. C++26 will have optional references. So we will, and you can thank the gentleman behind you. Oh, did you not? I thought it was yours. I apologize. Oh, I thought you were responsible. In that case, you get no credit. Okay. This next element function allows us to single step through sequences. It means that we can easily transition from the default push-based internal iteration to pull-based iteration, right? We can have the best of both worlds. We can have the speed and the optimizability, if that's a word, of internal iteration, but we can also do this single stepping thing, right? We have the best of both worlds. We can possibly have it all. So I mentioned this already, but iteration contexts are kind of the low-level thing. End users, typically, we're going to have algorithms and adapters on high-level iterables. Okay. So how do we implement our own iterable? Well, I've made it as simple as I could possibly make it. We have to implement one function. Okay. We have to write a function called iterate, which returns us an iteration context. Okay. And optionally, if we want to, we can also provide a const overload of iterate to do const iteration, that is, give us const access to the elements. Okay, so here's a little struct that I want to turn into an iterable. Well, handily, I already wrote an iteration context that will do this. So we want to turn it into an iterable. We can do this by specializing a class template called Flux iterable traits. So we provide a specialization of this class template for our ints class, and inside there, we implement an iterate function, and this iterate function, all it does is return the ints iteration context that we already saw. And this is fine, this is quite easy, but there's an even easier way to do it, because we can actually just have a member function called iterate, and provided this returns you an iteration context, this ints struct is now considered an iterable and can be used with various algorithms. Generally speaking, you don't have a separate iteration context type. What you would normally do is actually have it as a kind of nested type inside your iterable. Right, so this is a more realistic example. So this is just the exact same iteration context you already saw, but we have it as kind of a nested type inside the ints. Right, so this is actually a pretty realistic example of how you would write something similar to like views iota in this scheme. I was going to talk about implementing algorithms on iterables. I'm going to skip this, I'm afraid, because I'm running a bit short of time. But basically, you can write a fold in terms of run while, and fold is like the granddaddy of most algorithms that you want to do. But as I mentioned, we also have this single stepping. So equal, or in general, if you're iterating over more than one thing at a time, you can't use internal iteration. But because we have this next element function, we can do things like implement the equal algorithm. So again, I won't go through it all, but I will tell you that it is possible to do and that it works very nicely. So we can write basically all of the algorithms that we could write on single pass ranges, single pass sequences in Flux, we can do with this new iterable iteration context stuff. It is super fast. We get the optimization opportunities of internal iteration, but we can step back to doing step-by-step iteration when we need to. Okay, works really, really well. And of course, it's not just about calling algorithms. We want to be able to build up these data pipelines, right, that we can do with ranges, that we can do with Flux. Filter, transform, chunk, group by, etc., etc. So as ever, writing these lazy adapters, it is a bit more work than just writing a terminal algorithm, right? You have to set up a wrapper type and stuff. Generally, it's easier with this scheme than it was in Flux v1, and it's a lot easier than it is in C++20 ranges. I don't know if has anybody here actually written their own like range adapters? Yeah, Zach. Yeah, no. It's painful, but I'm going to show you now. I'm going to show you an iterable adapter on the screen in just a moment. Show you how simple it is. So typically, what we do is we write some some adapter type that holds an instance of the base iterable, right? So this is the same as like transform view does, for example. And then the iteration context for the adapted iterable will hold an instance of the iteration context of the base iterable, and in the run while implementation, it will call run while on the base, but with a modified predicate, right? This is kind of the secret sauce for how these pipelines become so well optimized. Okay. So I'm going to show you the filter adapter because that's kind of the most essential of them all, I think. So how do we actually write this? So we have a filter adapter that takes an iterable base, and the filter adapter has its own iteration context type. And this here, in this case, is templated on the base context type. Okay. It holds an instance of that, and it also, we take a copy of the filter function. Our element type is the same as the element type of the base. Okay, makes sense. And now we're going to implement run while. So how do we do this? Well, as I've already said, what we do typically is we call run while on our base context, and we pass it a modified predicate. So in this case, what does our predicate do? Well, it says, okay, if the element passes the filter, then I'm going to pass my user's predicate in. I'm going to call that with the element, and otherwise, if we don't pass the filter, then I just want you to continue. Okay. And it should be forward ln. There's a typo on this slide, very annoyingly. Yeah, that should be ln there. Apologies. And then we also need to close all of our curlies. Okay, so call run while on the base context, get great performance. That's kind of the takeaway. So this is the members, this is the context type. All the rest of what we do to make this the filter adapter is we need to provide an iterate function that just returns our context type. And again, we initialize the base context by calling flux iterate on our base member. And we actually take a reference to the filter function as well. So we've got our regular mutable iterate, and if the base supports const iteration, then we do that as well. All right. I'm rushing because I really want to show you this, because this is the important bit. I want to go back to this print evens example. So we saw how we expand all this out for ranges and how it leads to sort of ugly code, right? I want to see what happens if we do this now with the Flux library, with this iteration context stuff. Okay. So there are many ways of writing it. This is just one that flows quite well if you write it like this. Okay, we set up our flux filter and we're going to call for each, and for each element in the filter, we're going to print I. Okay, so what does for each do? Well, it initializes an iteration context and then it calls run while on that context, passing it a predicate that always returns true, right? Because for each, we never want to break out of it early. Okay, well, we've just seen what the filter adapter looks like. What does it look like? What does the filter context look like? Well, it just holds an instance of the base iteration context. Okay, what is our base context in this case? Well, our base is just a vector, right? So we're just going to use the range iteration context that we've already seen. Okay, we're going to call the range iteration context, and then we're going to call run while on that, passing in the modified predicate. Okay, so it expands again to something roughly like this. This looks a bit complicated, but these are all kind of nested lambdas. This is code that the compiler is generating anyway. Right? The compiler is generating this. It can see straight through it. It can understand what's going on and can simplify this right down to something that looks like this. And then, okay, we've already seen this. What does run while do on a range iteration context? Well, it expands to something like this. It says, well, iter is not equal to last. Okay, if the predicate returns false, we're going to break. That's the predicate we're using in this case. But again, the compiler can see that this is a predicate that always returns true. So it doesn't need any of that. It can optimize it to something that looks like this. And this, to me, looks very, very much like what we started with, right? We are incrementing the iterator in a slightly different place, but other than that, this is pretty much what we started with the handwritten code, right? That's what I think. Is that what the compiler thinks? There is a way to find out. I don't know who came up with it. Okay, so this time, again, we've got, this is again using sums rather than print because it just demonstrates the points better. We've got the imperative version on the top, just as we did before. This time we've got the flux version, the flux development version on the bottom. And you can see that this time we're getting this lovely vectorized SIMD code on both sides. The compiler has been able to chop through all of these iteration contexts, all of that. We're getting this lovely, highly optimized internal iteration code. Okay, I'm going to skip a whole bunch of stuff now because I have spent way too long talking about things I wasn't going to talk about. And just in a couple of minutes, just going to race through talking about the other side of the thing is collections. So I was always going to have a shorter period about part about collections because this isn't really new. If you've seen the previous Flux talk, this is kind of the same, just cleaned up. So basically, the idea is that we have these bounds checked positions. So a position is an associated type of a collection, and it represents a place, right? So previously we called them cursors. Now we're calling them positions. They're pretty much the same thing. It's like a generalization of an array index. And this is contrasted with iterators, which are a generalization of array pointers. And I said this about cursors earlier, and it remains true. Unlike iterators, position objects, they're not smart, right? They don't know how to increment or dereference themselves. Their only role is to serve as a way of saying how far are we from the start. That is literally all a position can do, right? It means that if you are holding on to a position and the collection that you are referring to, like it dies, well, there's nothing you can do with this position object, right? It's not like an iterator where you can, where it becomes dangling, and if you dereference it, you die, right? It's basically like holding on to an int, right? It's fine. So position objects are regular types. We need them to be default constructible. We want them to be copyable. This is very useful in algorithms. We want them to be equality comparable so that we can say, are these two positions, are they the same place in the same sequence or the same place in a sequence? Okay, what's new in the new version of Flux compared to the previous version with cursors, this is why I wanted to get to this, is that now in the new version, all positions must have a strict social order, right? Positions must be ordered, i.e. we can say, is P1 less than P2? And if so, then P1's an earlier position in the sequence. Okay, so this is, we required this for random access sequences previously, but now we require it for all things, for all collections. And the reason for this is for safety. So with ordered positions, we can easily, uniformly, universally perform bounds checking for all collections all the time. Okay. And in particular, and this is really the reason I added it, we can easily perform bounds checking for arbitrary slices of collections. And what this means is that if you have some collection and you pass mutable slices to different threads, we want to be very careful to make sure that none of those threads are overstepping their bounds. Okay. With this, you can now perform that bounds checking on arbitrary slices. Okay. Skip right to the end and I would just one slide about ranges compatibility, because as I mentioned, a good interop story with STL containers and algorithms is essential. We've already seen this. We can write an iteration context for any input range, right? And this means that every C++20 input range is automatically iterable, right? You can just start using it. I didn't get to talk about reverse iterables, but every bidirectional sequence is also reverse iterable. What about in the other direction? Okay, I've written my Flux iterable. How can I use that with ranges? Yes, you can. You can pass it through that we have this adapter called asRange. And what this means is if you use this asRange adapter, this is going to give you back, it's not a view technically, but you can think of it as being like a view, and you can use that with ranges algorithms if you want to. As it happens, for various reasons, we can actually use a range for loop directly, because the rules for range for loops are slightly weaker than they are for range algorithms, so we take advantage of that. You can use iterables directly with the range for loop without having to use any sort of adapter. So that's really nice, because that's kind of a lot of what people want to do. So that's for iterables. For collections, every collection is automatically at least a forward range, and every size random access range is automatically a collection, right? Because these are the things that we can do bounds checking on. Collections must be bounds checked, and we can do that with random access ranges, or sized random access ranges, because we can offset the iterators. Okay, faster, safer, better. Well, I mean, Flux today offers unrivaled performance. I'm going to say, just. When you're on the fast path, the iterable protocol allows us to expand this fast path to make it broader, to have more people on it, and all going fast in the same direction. It's great. Iteration contexts are safer. They know their own bounds. They don't overstep them. And the collection protocol gives us universal, safe, bounds-checked generic element access for multipass sequences. Okay, faster, safer, better, easier to use. Thank you.